Hi, welcome everybody. Thank you so much for joining us for another Sky Tonight Planetarium show. My name is Andrea Decker and I have the pleasure of representing the Fleet Science Center. For everybody who's been to a Sky Tonight before, thank you so much and welcome back. For anybody who's new here, we're so glad you're here. And to give you a little bit of background information, Sky Tonight is our monthly planetarium show that normally takes place in our beautiful Hike of Domes Theater, where you literally sit under the stars and we fly you through the universe, and it's absolutely amazing. Unfortunately, that is not happening right now. I think we all know why, so no need to mention that again. The good news is the fleet is open again, but we're on a limited schedule still. So we are open from Friday through Monday. So yay, fleet being back, super excited. So if you want to visit us, we would love to have you. The IMAX theater is open, our exhibits are open. Of course, we require masks, social distancing, and we have an extended cleaning schedule so that we are able to clean every exhibit once every hour. So we do everything we can to keep you safe when you come visit us. So we hope that you do. We are not quite sure when we go back with Sky Tonight, but it looks like if the numbers stay as they are, and it looks like July should be a for sure bet at this point. I'm just going to say it's a for sure bet. We're just not sure if we can do it June. So we're trying our hardest to see if we can make it for June. If not, then July, I'm going to say now we should be back, all things continuing as well as they have in the past couple of weeks. So I hope that is some exciting news for you too. It sure is for us. I know Lisa can't wait to get back into the dome. And we would be excited to bring that show back because it also allows you to do some stargazing out on the Prado right after. Normally the San Diego Astronomy Association puts up telescopes outside, and of course none of that has happened in the pandemic. But it just makes for a wonderful evening out in beautiful Balboa Park, looking at the stars in the dome and then seeing them in real life yet again is awesome. All right. I think that's kind of what I have to say. Lisa's going to give her presentation as she always does. She's going to start off with some of the news in astronomy and space travel and whatever there is to report. Then she's going to go and lead us through the sky tonight. So we're going to look at the constellations as they are, as if you would go out at 8 o'clock. So right after the show, you can go. It should be clear. It's clear, Louisa. So you should be able to go out and see a little bit of what Lisa is telling you tonight. And then after that, we're going to get into the topic of this month, which is colors in space. And once Lisa is done, we're going to do the Q&A. And we do that through the Q&A function. So if you have the Q&A button at the bottom of your screen, you can open that up, type in your question and send it off. I will keep an eye on the questions even during Lisa's presentation. We normally try to get to all the questions at the end of the presentation, but if there's something that we can take in between, then we will do that. I encourage you to type the question up once it pops into your mind so you don't forget. You can send the questions anytime you're ready to do so. And during the Q&A, I'm going to open a poll. It's our little audience survey, so keep an eye out for that. And it's just a little thing you can do while you listen to the Q&A. All right, I don't want to take too much time from our awesome Lisa. She's our resident astronomer and also a physics professor at the San Diego City College. So Lisa, take it away.
Thank you so much, Andrea. Hello, everyone. As always, I am so happy to be here with you, being able to safely share the sky with you until we can get back under the dome together. Let me go ahead and bring up my screen. All right. So we are going to start off with some recent news. I like to keep you up to date on what's happened since we were last together. And so what is this messy graphic? All right. So there is a red donut looking thing at the bottom of the screen. You might recognize that as the first image of a black hole in the galaxy M87 that was released April 2019. Now, everything else on the screen is also an image of that same galaxy, but at different wavelengths. They wanted to be able to study this black hole and its effect on its surroundings because it actually emits a jet. out on into space. And you can see that jet. That's what the long lines are in this graphic. And so in order to observe it at all wavelengths at about the same time, this is actually 19 observatories worth of data, multiple wavelengths. We're looking at it in visible light, ultraviolet light, X-rays, high energy gamma rays, all the way down to radio waves, infrared. And so we're actually doing a multi-wavelength study of this black hole and its effect on the jets all at contemporaneously. And so this data was released last month, and it is the largest simultaneous observing campaign ever undertaken on a black hole with jets, and also the first time we've ever been able to do this for one that we can actually see, the black hole. All right, what's next for us? So the next thing I want to show you is a little bit closer to home. What you're seeing here is the orbit of the Parker Solar Probe. The Parker Solar Probe is orbiting the sun and getting really great data for us, and its goal is to get ever closer and closer to the sun. And on February 20th, via a gravitational assist from the planet Venus, it altered its approach towards the sun to where it reached its closest approach to the sun so far, just in late April, coming into within about 6.5 million miles of the sun. It sounds really big to you. That's really close to the sun, though. And it was going about 330,000 miles per hour. So it makes it the fastest spacecraft now. It's not the fastest spacecraft we ever launched. The launch speed for the fastest spacecraft, that belongs to the New Horizons spacecraft that we sent out to Pluto. But now this has gotten accelerated by the sun's gravity up to the fastest speed in flight. And so it has broken its own records now for fastest speed and proximity to the sun. And so this spacecraft keeps sending back very interesting data for people who study the sun, but it's really fantastic that we're actually seeing it be able to survive getting to these tremendous speeds and so close to the sun. It's really kind of interesting. All right, so some of you may remember back in October, NASA's Osiris-Rex spacecraft did what they call a touch and go mission to the asteroid Bennu. That asteroid had been orbited by the Osiris-Rex spacecraft for a while, so it could find a suitable spot on the surface of the asteroid in order to do the sample. Because you might notice there's a lot of rocks in this image, and what we're seeing here is the before and after of this region of this asteroid. This site was called Nightingale. You can see the first image is where just the circle is. And in the second image, you can see how far that boulder moved. That boulder moved about 40 feet due to the expulsion of gas by this touch and go mission, because the way that this worked was that it collected samples by blowing gas onto the surface of the asteroid and kicking up the debris and taking those samples. So we can see how the Osiris-Rex spacecraft in this maneuver disturbed the environment of this asteroid. And it can do that for a couple of reasons. This is the smallest asteroid we've ever orbited. It has a low gravity. It was just a little bit easier to give this material a kick. Now, this spacecraft, it collected samples, so obviously it wants to bring the samples back to scientists. And so this mission has ended its science duties, and next week, it's supposed to happen on May 10th, or at least it's scheduled for May 10th. The Osiris-Rex spacecraft will leave the asteroid Bennu on its way back to Earth, where it will be returning the samples it collected in September of 2023. And so this is a sample return mission, and you can see now what it did to the asteroid as it was collecting those samples. There is a total lunar eclipse this month. And as you can see here in this diagram, here in San Diego, we are under a region that says most of eclipse visible. We will be able to see the moon totally eclipsed from here in San Diego, but it will still be in partial eclipse as the moon sets at that time. So when is this happening? It's happening overnight on May 26th. Actually, for us, it's really happening early morning. And so the total eclipse, so the moon, as the moon's shadow starts, or excuse me, as the Earth's shadow starts to fall on the moon, the eclipse technically begins, but the first touch of the Earth's shadow is really light. So unless you're knowing what you're looking for, you're not really going to notice it as a casual viewer. The total eclipse begins at around 4:11 in the morning of May 26th. The maximum eclipse is around 4:18, and the end of the maximum of eclipse will be at around 4:25. Now, it'll be partially eclipsed before that and after that, but the moon will set, at about 5 something, like all close to 6 a.m. So if you're interested in watching it, you're going to have to be an early riser here in San Diego, or if you're like me, just stay up late and watch it as in the early morning. So you're going to, for most of us, this means we're probably going to make an effort to see this one instead of just going outside at night. But there is a total solar eclipse visible from San Diego later this month, May 26th. And then in April, the Hubble Space Telescope celebrated its 31st anniversary since it launched. Can you believe that? It's been up there functioning for 31 years. And every year they put out a anniversary image. And the anniversary image this year is of the star AG Carina, which means it's in the constellation Carina, which is a constellation in the southern hemisphere sky. And it's an example of something called a luminous blue variable, which means it's really bright and blue, but it varies in the amount of light that it puts out. And part of that is because it is such a large luminous star that its energy output can be a little bit chaotic, and it has these outbursts. And what you're seeing in this image is that star surrounded by the outer layers of material that it's burst off in previous eruptions in its time. Stars like this one are actually rare. We've counted only about 50 of them in our local group of galaxies. It shines with the brightness of about 1 million times the brightness of our own sun. It's about 70 times the mass of our sun. So this is a young star, because stars with that mass burn through their fuel so quickly they don't live very long. And so we all, in astronomy, we refer to these as stars that live fast and die young. And so that's one of the reasons why they're rare. They just don't hang out for very long. They don't last very long. And so this star is located about 20,000 light years away from the Earth. And the nebula that you're seeing there, the gaseous ring around the star from its previous outburst, is about 5 light years across. And so happy 31st anniversary to the Hubble Space Telescope. May you keep going a few more years. And that brings us to tonight's sky. As Andrea mentioned, I usually do this for 8 o'clock, but as we're getting into the summer and it's sunlight is annoyingly longer days, right? So I've switched this to 9 o'clock this evening and to let twilight abate a bit more. And so this is the sky as you would see it at around 9 o'clock tonight from here in San Diego. South is to the bottom of the screen, north is to the top of the screen, east is to your left, and west is to your right. And I always like to start off with all the pretty pictures, because we are surrounded by constellations day and night. And these are mythological stories that help us put together the stars on the sky into patterns that we can recognize and that we can use to communicate with each other where these things are on the sky. But and then we give them names to help us remember them. And we're going to go through some of the more prominent ones on here together tonight. But when you go outside, you don't see the pretty pictures, you see the dots, and the brain likes to connect the dots. So when we go through and we talk about the constellations, instead of focusing on the pretty images, we actually we take a look at the connecting the dots themselves. And so here are the constellations. So let's go ahead and start with one that you should be more familiar with, or at least that maybe you've heard of part of, which is Ursa Major, the Big Bear, which is one of the larger constellations on the sky. It is actually the third largest of the 88 constellations that astronomers use today. And you probably know this better as the Big Dipper. And so the Big Dipper is made up of the bright stars that make up the back of the bear, the Big Bear. And this is a prominent, what we call an asterism in the northern part of our sky. And it is a good way to go out and orient yourself on the sky. The two stars that are going pretty much straight up on the screen next to the letter R, those two stars actually point upward to where the North Star is, Polaris. We call those the pointer stars. Now, the way we have this extended on our screen, we actually can't see the North Star. Sorry. That would make it a really weird aspect ratio if I did that. But that's how you would find North. Take those two pointer stars, those two stars next to the R, follow them towards the North, and that would actually give you the direction of where true North is on the sky. Let's move on to another constellation. Now, this one is also in the northern sky, and it takes up sort of a large part of the sky, but I'm betting you haven't seen it because it is extremely faint. And this is the constellation Lynx. And it's not associated with any ancient myths because this is something that is considered to be a modern constellation because it was made in the 17th century in a catalog. So let me tell you a little bit about the history of the constellations. The constellations that we use today, a lot of them date back about 2,000 years to a catalog made by the astronomer Ptolemy. He made 48 constellations out of the bright stars that he was able to see with the naked eye in the northern hemisphere sky. But that he just connected the bright dots, let's put it that way. But as time went on, and astronomers also wanted to use these constellations to give us direction on the sky, a placement on the sky, it was realized that it would be really handy to have some constellations in the faint regions. And so in the 17th century, an astronomer named Johannes Hevelius actually came up with a catalog where he filled a lot of the gaps. And so there's an influx of constellations that were made at that time. And so the constellation Lynx was named after the lynx because it's an animal that apparently has really good eyesight. And these stars are so faint, you would need the eyes of a lynx to see them. So that is a constellation that is hard to see from a metropolitan area like San Diego. But if you're out somewhere in a darker sky, you should be able to see it to the west of the Big Dipper. Now, in another part of the sky, there's a huge constellation in the southern part of the sky called Hydra, the sea serpent. And it is actually the largest of the 88 constellations that astronomers use today. And the brightest star that you can see in those dots is named Alphard. It comes from an Arabic term that means the solitary one, because it is the brightest star over in that dark patch of the sky. And that star is about 180 light years from our solar system. A light year is the distance that light travels in a year, and light travels really fast in a year and is a long time. So it's a really big distance. Another way to think of it is that if you're looking at a star that is 180 light years away, you're not seeing it as it is, but rather as it was 180 years ago. So if you go outside tonight and you manage to see Alphard up in the southern part of the sky, you'd want to be looking low towards the southern part of the sky. You're seeing something as a star's light that took over almost 200 years to get to you. So you're seeing it as it was almost 200 years in the past. And so I always like to go out and think of that when I'm outside looking up at the stars in the sky, because you're seeing the history of the universe is coming to you while we sit here looking up at the sky. Here's another constellation that a lot of people haven't heard of. This time of year, at this time of night, there's a lot of these faint connect the dot constellations up in the sky. This one is Canis Venetici. It's the two hunting dogs. And this one actually is a weird constellation in that these two stars that make up the brightest part of it were actually part of Ursa Major, and then got redrawn in catalogs and ended up in different constellations and then got left out of constellations. And so a lot of the major constellations have remained pretty fixed over the years, but these fainter stars and some of them have kind of shifted around over time. And so because these stars aren't bright, they actually just got misidentified as part of a constellation in a translation from one catalog to another. And so this was made its own separate constellation in the 17th century, although it used to be part of other more famous ones. Then we have Coma Berenice's hair, which has sort of an interesting history. It's named after a queen who was worried about her husband, the king, when he was sent off to war. And she was very proud of her hair, but she prayed to the goddess Aphrodite, if you bring my husband safely back from war, I will I will cut my hair and I will give my hair to you. And so when the husband returned, the queen, Berenice, she did as she promised. She cut her hair and donated it and placed it at the temple of Aphrodite. And it was so pleasing Aphrodite that it was put up into the sky to commemorate her gift. And so this grouping of stars is named Coma Berenices, or Berenice's hair. This constellation that kind of looks like an ice cream cone. I know astronomers are supposed to say it looks like a kite. It looks like an ice cream cone. It's up during the summer time. It's an ice cream cone. This is Boötes, the herdsman. The brightest star that you can see there at the base of the ice cream cone is named Arcturus. Its name comes from a phrase that means guardian of the bear because of its proximity to Ursa Major. And it is a star that you can see that's about 37 light years away from our solar system. And then the rest of the constellations I want to talk about follow along a path on the sky that is called the ecliptic. Now you'll notice this line that I put up here on the sky has the months of the year. And so what you're seeing here is the months and days of the year. But what's on them? Well, that's where the sun would be on any given day of the year. So as I have this set for tonight, and we're at the beginning of May, you can see that the sun should always be already be below the western horizon because it's already set by 9 o'clock tonight. But this is the path of the sun across the sky, and the moon and the planets hang out in this part of the sky as well. And so the constellations along this path have gained cultural significance over time. In fact, these are the signs of the zodiac. And so we are going to talk about the zodiac signs going from east to west across the sky. So that makes us start with Libra. Libra is the only zodiac sign that does not symbolize a living creature. It's the scales, or scales of, we often think of it as being scales of justice or scales of balance of some sort. The brightest star in Libra is Zubin Ganubi, and it is a binary star, actually, that is located about 77 light years from our solar system. The next sign of the zodiac, going over to the west, is Virgo the Maiden. It is the second largest of the constellations on the sky. Its brightest star is named Spica, which comes from a phrase for ear of wheat. Virgo is a constellation associated with fertility, and so the wheat and the harvest go along with that motif. Spica is the 15th brightest star in the nighttime sky. It's located about 260 light years away from our solar system. The next sign of the zodiac over to the west is Leo, the lion. Now, this one, the stars are bright enough that you can even see it from a metropolitan area like San Diego. You're not just seeing one of the stars, you can see a lot of the stars. The front of the lion, it looks like a backwards question mark. The brightest star at the base of that backwards question mark is Regulus. It's the brightest star in Leo, and its name comes from a phrase that means prince or little king. The second brightest star in Leo is at the tail of the lion. And you can also see that triangle is being prominent on the sky with the naked eye as well. And that brightest star, or that bright star at the edge of the tail, is named the Nebula. And it's about 36 light years from our solar system. The next sign of the zodiac over to the west is the constellation Cancer, the crab. Now, this is not easily visible with the naked eye. So if you wanted to go look for it tonight and your sky is clear, I hear it's clear out in La Mesa, but I'm here over in coastal San Diego, and I look out my window and I see some marine layer coming in. So wish us luck out here to look at the sky. This one's actually really hard to see from a city. So if I wanted to go look for it, I would look to the west of Leo. I would actually look for Leo first and then pan to the west. Cancer is the crab identified that actually appeared while Heracles was fighting the Hydra, and the Cancer, the crab, bit Heracles, and so Heracles killed it because he was annoyed that he got bit by it. And then Hera, who didn't like Heracles, said, I'm just going to throw this crab up into the sky to be your nemesis. So the crab is always up there. And so Heracles could not get away from the crab. I love stories like that. It's all over the sky. And then the final sign of the zodiac that is visible tonight, setting over in the western horizon a little after 9 tonight, is Gemini the Twins. It's named after the twins because those two bright stars next to the letter G, they really do look very similar to each other with the naked eye. So they're named Castor and Pollux after famous twins from Roman mythology. But what I've always found interesting is that they look so similar to each other that various cultures actually thought that they were twins. And this region of the sky was referred to as the Great Twins in Babylonian astronomy, which predates Greek and Roman astronomy. So it's kind of interesting to see how the mythology continues and the ideas of what the perception. This also gives us an idea that these two stars have appeared very similar in brightness to each other for several thousand years at this point. And so that's just, we see how long the lifetimes of stars can be and how similar they can look. And I also like it because although they look like twins to us, one of them is twice as far away from our solar system as the other. And so they are not the same brightness because they're the same distance. We don't have, you don't have good distance judgment or good depth perception on the sky. And part of that's because not all stars emit the same amount of light. And over in Gemini tonight, Mars is hanging out over there. And so it is the one planet visible with a naked eye that's up in the early evening sky this evening. So I wanted to take some time to talk about Mars. And Mars is really, I'm just going to focus on some of the results just from the Perseverance rover, because there's been lots of stuff going on Mars. So we're going to go back to a little bit of current events talking about Mars. So one of the things that happened recently was the MOXIE instrument on the Perseverance rover, which is what you're taking a look at here is the schematic of. It did a really interesting experiment. So MOXIE stands for, and I'm going to look at my notes for this because I can't remember all these acronyms. Mars Oxygen in Situ Resource Utilization Experiment. So I think you can forgive me for not actually having that completely memorized. But the idea is that this instrument is taking in the carbon dioxide from the Martian atmosphere and producing oxygen from it. And so for the first time ever, we have taken a sample of another world's atmosphere and created oxygen from it, or basically separated the carbon and done the experiment and separated the oxygen out of the carbon dioxide. After an hour of operation, the total oxygen produced was about 5.4 grams. So this isn't pumping out huge amounts of oxygen, but this is something that we're looking at in case we do send astronauts to Mars. Do we have to take all the oxygen that we would need for their entire mission, or can we produce some of it there? And so this happened for the first time on April 20th. And so this is a very recent experiment. Oh, and then the other thing, I'm going to show you so many images, I can't stop myself. All right. So Perseverance had a helicopter on it. This helicopter's name is Ingenuity. And that's the little thing down here. Oh, look, it's spinning. So it's starting to spin its rotors. And now it is going to take off. And it's going to hover. And then it's not just going to hover there, it's actually also going to turn. Look, it executed a turn. And now it's going to land back down again. And so this is a video taken by the Perseverance rover of this helicopter that it carried with it. And this is the first powered controlled flight on another world. And so we've never done this before. And now we've actually done it several times. So in this first flight, it only got up to an altitude of about 10 feet, turned around, sat back down. But there's been other flights since then. And so this is its images from its third flight, and you can actually see its shadow. So there's a camera on the helicopter as well. And so it took this set of images. Like we're seeing a helicopter shadow on another world. And then another thing it did on its third flight was it also took images from above the surface. Now, the helicopter on Ingenuity is actually sort of a test. It's not sent there to actually do science. It's sent there to do engineering testing because we're trying to see what we can do with a helicopter. Right now, currently, we've been able to take images really close to the ground, basically on the ground from landers and rovers. We've been able to take images of Mars from orbiters, so in orbit around Mars, but we haven't been ever taken pictures really in flight regularly at sort of this different altitudes like this. Oh, have you seen the interesting thing up in the top left? Did you see it managed to take a picture of the Perseverance Rover? Look at that. Look at that. And I know I'm squeaking. I'm squeaking about a helicopter on Mars. I should have warned you that there would be squeaking. And then one more image here. You can see this dot up here. This is another picture. This was during the fourth flight on April 30th. So where the Perseverance Rover took a picture of it. This set of test flights have gone so well that they're going to start changing the mode of operations. The first thing was just to see if we could fly. The Martian atmosphere is incredibly thin. So trying to do powered flight, controlled flight with rotors is actually hard. And so this was sort of proof of concept. Can it be done? Now what they're going to start doing is sending it further, even further, and maybe having it start to scout like which would be a good way to send the rover next, which is one of the things that you would ideally want these helicopter missions to do. So anyway, I think I've squeaked at you about a Mars helicopter long enough, but I really have found this fascinating. So hopefully this will allow us to do more exploration, more efficient exploration of the red planet. But why do we call it red? Okay, so let's talk about colors in space. So, okay, happy belated Star Wars Day. It was Star Wars Day yesterday. For me, it's Star Wars Day every day. And so this is a still from The Last Jedi, Star Wars The Last Jedi. And it was in the trailers and in the publicity stills because it's a really eye-catching image, right? Like you see this really stark white plane, but it's kicking up red dust. And in the movie itself, we actually see this character taste the red stuff, which, believe it or not, is one of the first things I would have been tempted to do, because halite crystals, salt crystals here on Earth often have a pink tinge to them. And so this character actually licks this red stuff and says salt. And his name is Salty in the credits. Not kidding. And this is, I'm going to argue, the first time we've ever seen science done in a Star Wars movie, because he had a hypothesis and he tested his hypothesis through an experiment, not one I would necessarily recommend. But that's because he saw the color and said, maybe this color has told me something about it. Now, usually in space, we can't just go take a taste of something. Astronomers really depend on the light from distant objects to give us information. And so we're going to talk a little bit tonight about how that light and how it relates to color can tell us something. What you're seeing here, I'm not going to show you tons of graphs, I promise, but you're seeing a red star, a yellow star, and a blue star, and how their intensity or their brightness as a function of wavelength is different. And the way it differs is a function of their temperature. And so we can actually study the relationships between brightness and wavelength and where they peak, and where that intensity peaks. That actually can uniquely give me the temperature of the object. So I know that red stars are cooler than yellow stars, and that yellow stars are cooler than blue stars. So that if I were to go outside and look at Orion, which we can't really do tonight because it's a winter constellation, but next, I always like to use this as an example because there is a red star, Betelgeuse, at the top left shoulder, and a blue star, Rigel, at its bottom right foot, that when you take a look at them up in the sky with your eye, they're pretty much identical brightnesses, but they're also bright enough that you can tell the difference in color between them. And when you go outside, I like, oh, Betelgeuse is red. It is a cooler star than the blue star Rigel. And so you can tell relative temperatures by their colors. Now that brings us to the sun. This is an image of the sun from Big Bear Observatory, Big Bear Solar Observatory. If you've ever been up at Big Bear Lake, you may have noticed a solar observatory out on the edge of the lake. This is a visible light image. This is what our sun looks like. And you're saying, well, isn't this a black and white image? So this is the sun emitting white light. But isn't the sun yellow? Well, here's an image of the sun from space. And you might notice that the sun looks awfully white here. Our sun actually emits, is at a temperature, a surface temperature, where the light that it emits is actually fairly white in color, an almost equal contribution of all colors. Why do we think of it as yellow? Like if you were to pick up a crayon to draw the sun, you would most likely pick up a yellow crayon. It is likely due to the fact that our atmosphere scatters blue light. That's why the sky is blue. And when it scatters the blue light, it leaves the light coming directly to us a little bit more red. And so the sun looks a little bit more yellow to us when you look at it. Although you never look directly at it, we don't condone that, right? But your instinct of what the color of the sun is slightly yellow. What else can we get from the colors of and the light from stars? Here we have what we call chemical spectra. So we can take light and pass it through a prism, and it'll break the light up to all the colors of the rainbow. And that's that continuous spectrum you have at the very top of the screen. But if I take light just from hydrogen gas or heated helium gas or nitrogen, I don't get all the colors of the rainbow. I get bright lines of light of different colors at very specific wavelengths. And you'll notice for none of the elements or carbon monoxide, a molecule that we have here for you, none of them look the same. None of the patterns look the same. And so these chemical spectra are like fingerprints for elements and molecules. They're unique. And so if I can get the light from a distant object, I can tell what it's made from. So I can show you the spectra of stars. These are the this is the spectra of the 5 brightest stars making up the W of the constellation Cassiopeia. And you'll notice that none of them look completely identical to each other. And when astronomers study them, we can tell that stars are almost completely hydrogen and helium, but with different amounts of different elements that help us make these patterns unique, different temperatures that help make these patterns unique. And so we get what we call spectral classifications of stars, which are those letters you're seeing at the red end of the spectrum. So taking a look at the light and the colors from stars help us learn about the stars. You'll also notice that they're not all equal in brightness at all colors. And so these stars, although when you look up at them in the sky, they appear just like white light to you, stars actually have colors. But with the exceptions of stars that are really bright in our sky, like Betelgeuse and Rigel, your eyes aren't picking up enough light from them to trigger your color receptors. So your eyes are basically saying light, no light. Your eyes are working as sort of a binary switch. But if you take images through telescopes, you can pick up more of the colors of stars, which is kind of what you're seeing behind me tonight, a Hubble Space Telescope image of a cluster of stars, and you can see all the colors of stars there. And then there's nebulae out in space that have colors that can tell us about them too. This is a nebula called the Witch's Head Nebula, because you can see sort of the profile of what people have traditionally thought might look like a witch. And this is an example of something called a reflection nebula. The tiny dust particles in the nebula are scattering the blue light from that nearby star. And so it's like it's scattering or reflecting the light of that star, where that's where the name reflection comes from. And we see some of these reflection nebula near what we call emission nebula. This is a famous nebula in the sky called the Trifid Nebula. And you see blue reflection nebulae and a reddish, what we call emission nebula. Now, what is the red emission nebula? Tell me. Well, I can take a look at its chemical makeup because this is light that is being emitted by this gas. And these nebula tend to look red in true color images because they're mostly hydrogen. And if I were to bring a tube of hydrogen gas into the planetarium with me and heat it up, it would glow red to you to the naked eye. And so that's what you're seeing here. And this is a type of nebula where the stars that you're seeing down at the heart of it, in the center of it, those stars have recently formed out of this gas and dust. And now the leftover gas and dust is being heated up by these newborn stars, causing it to glow. So the emission nebula should be red to the naked eye. But lots of times when you see pretty Hubble Space Telescope images, you're seeing blues and greens and reds. And I remember having, I have I have a professor from grad school who argues that these are true color images. Some people call these Hubble Space Telescope false color images, and I'm going to argue to you that they are true false color images or false true color images, either way. This is actually the 28th anniversary image from the Hubble Space Telescope highlighting an emission nebula. So to the naked eye, if you could see the light being emitted, it would look red to you. But what we do with the Hubble Space Telescope is, you know how if you have a color printer at home, you tend to have 3 colors that are used to mix to do all the colors. On the Hubble Space Telescope, they tend to make images using 3 primary filters. And when you co-add them equally, you get this sort of coloration. But each of those filters is highlighting light from a different chemical element, and they are not, the amount of those chemical elements is not equally weighted. So are they all there emitting that light? Yes. So true, right? But this kind of coadds them, making them look like they're in equal amounts. And is that true? Well, that's false. So you see kind of the idea there. But the reason why you would coadd them is that the brighter parts of this image actually are hotter. The parts of this image that looks like the gas is less dense, a little wispier. It actually is. By co-adding the different chemical elements that are chosen for these filters in this way, you're actually getting some idea of the physics of what's going on. So astronomers can look at the color and take the light from these objects and get density. We can get whether or not there's a magnetic field. We can get the chemical composition. We can get all sorts of stuff about these objects. Now, I've been showing you nebulae far away. A little bit closer to home in our solar system, we tend to see things by reflected light. And so let's just remind ourselves of what reflected light does. If you are looking at a green leaf outside, it is getting the overall white light from the sun, and it is reflecting the green back to you. And so what you're seeing over on the right-hand side is something called absorbance as a function of wavelength for chlorophyll. Chlorophyll is really good at absorbing blue and purple, and it's really good at absorbing red. So what does it reflect back? It reflects back the green. And so even seeing stuff just by reflection, not necessarily emitting light itself, but the way it reflects light can tell us something about what it's made out of. And so as we look at the objects in our solar system, we do a lot of reflectance data collection. And so this is the planet Mercury. So we're going to go through the solar system starting near the sun. And this is kind of a true color image, more or less, of the planet Mercury. And it's darker than our moon overall. And the darker material on it actually turns out to be carbonaceous. A lot of it's actually graphitic or graphite, which is unexpected. But it's thought that the graphite could have crystallized out of the magma during an earlier, more volcanic stage of the planet itself. You'll also notice that we don't see as many craters on Mercury as we do on the moon because it's closer to the sun. And if it's an asteroid or something hurtling through space and it has a choice of hitting Mercury or the choice of hitting the sun's gravity is going to grab it. So we see fewer craters per square mile on the surface of Mercury, and slightly darker than the moon, but looking very similar to the moon otherwise. The next planet out from the sun is the planet Venus. and it has an incredibly thick atmosphere due to the runaway greenhouse effect, and it has a yellowish tinge to the atmosphere, likely due to the sulfur in its clouds. Although Venus's atmosphere is mostly carbon dioxide, the clouds in it contain droplets of sulfur dioxide, where the sulfur is probably from the outgassing from volcanoes earlier on in the history of Venus, although it could still have active volcanoes. It's just really hard to tell because in visible light, we actually can't see down to the surface. We're going to skip over the Earth for a minute and go to the next planet out from the sun, which is Mars, that red planet that we mentioned that the Perseverance Rover is on and that the Ingenuity helicopter is flying over. This is an image of Mars from Damian Peach, and he does amazing work with telescopes here on the ground. Mars is amazing to look at. It's got that ice cap in the southern hemisphere. You can see clouds up in the northern hemisphere. And it is reddish. It's noticeably reddish to the naked eye up in the sky. You see it as the bright red dot in this image because the iron in its rocks oxidizes with the oxygen in its thin atmosphere. And so you get sort of reddish rocks due to oxidation. Think of northern Arizona, northern New Mexico, the red in the rocks. That's what we think has made the Martian soil more reddish. And so therefore prominently red in the sky. Got its name after the god of war because of its blood red tinge in the sky. This is Jupiter. Isn't Jupiter gorgeous? This is an image from NASA's Juno spacecraft. And what you see here on Jupiter, these different colors are coming from different chemical elements in the clouds. So we get cloud mixing here. And the colors, we have sort of whitish clouds made out of ammonia. The reddish yellow clouds are ammonium hydrosulfide. There's water vapor clouds or water droplet clouds. And so the different chemical elements in the clouds of Jupiter and the way they interact with solar radiation and the different depths that we're seeing too in the cloud layers give Jupiter this amazing, amazing texture. When you take a look at Jupiter through a backyard telescope, you just see the stripes and some of the larger storms, those larger ovals there. This set of images are taken by a camera on the Juno spacecraft that is made by Malin Space Science Systems here in San Diego County. And the camera is identical to one of the ones on the Mars rovers. And so it's because the Juno spacecraft is getting really close to Jupiter in its orbit, we get to pick up these amazing details in the cloud layers. And then this is Saturn. This is the last mosaic image taken by the Cassini spacecraft before it ended its mission back in 2015, 2017. In any case, it was very sad when that mission ended. I'm still sad about it. And so the yellowish color here that you're seeing, the tinge to it in Saturn is the ammonia ice present in its atmosphere. And on the left, we have the planet Uranus, and on the right, we have the planet Neptune. And you'll notice that even though Jupiter, Saturn, Uranus, and Neptune are all what we refer to as Jovian planets, they're all mostly big balls of gas with giant rocky cores at their centers. They're very different in their coloration. And we have the chemical element in Uranus and Neptune that are giving them different colorations is methane. Methane, you may have heard, is a good greenhouse gas, which means it's good at absorbing infrared, but it's also good at absorbing red. And so if it's good at absorbing red, that means more blue light gets reflected back. And so the difference is about 1% difference in the atmosphere. I think if I recall, the atmosphere of Neptune has 3% methane and Uranus is 2% methane. And so you can see the more methane, the deeper blue the coloration is. So those are the planets of the solar system. Let's take a look at the moons real quick. And these are the 4 largest moons of Jupiter, the Galilean satellites. What I love about showing you images of the Galilean satellites is that the colors tell you that they are completely different surfaces from each other. And so when we take a closer up look at the one over on the left, Io, This yellows and oranges, once again, are sulfur compounds due to the volcanic activity. Io is the most volcanically active body in the solar system. Every time we've sent a spacecraft by it, it has been in eruption. And so the volcanic plumes are actually depositing sulfur compounds. And there's also a lava flow smoothing out the surfaces as well. And so we get all these subtle colorations, subtle and not so subtle colorations here on the surface due to volcanic compounds being emitted. And then this is one of the other Galilean satellites of Jupiter. This is the moon Europa, and it is about the same size as our own moon. And you see a surface here that is white with reddish cracks in it. And this is a surface of water ice and cracks in the ice. And if there's what look like cracks in the ice, so we have reason to suspect that there is a subsurface ocean underneath a crust or a surface crust of water ice. And that some of these reddish compounds that you see are coming up from fresh water, basically coming up in between the cracks and refreezing. And there have been some interesting organic elements discovered in those reddish cracks. So tells us a little bit of what's going on underneath the surface of water ice. And this is not the only moon in the solar system that has a surface of water ice. This is Enceladus, one of the moons of Saturn. And so you can see, once again, it's white, highly reflective color, some blue tinges in the cracks in the southern region. And what we don't think there's necessarily an entire subsurface ocean underneath this. You'll notice that there's more craters in the top part of the image than there is in the bottom part of the image, which means the surface in the bottom part of the image is actually younger. It's more recently formed. So there may actually be a reservoir or a large lake or something located in one part of this moon, but not the other. We know that there is subsurface water, liquid water, because this world has geyser activity. We've seen with the Cassini spacecraft liquid water geysers. And then that's not even necessarily the most interesting moon of Saturn. The light yellow part of the screen to the right, that's actually the planet Saturn. You can see the shadow of its rings falling on itself. That thin band going across this image is the ring seen on edge. And then the orange ball in the center is the largest moon of Saturn called Titan. And what you're seeing there is a thick, significant atmosphere. That's why it looks fuzzy and orange and we can't see down to the surface. And the coloration in its atmosphere is due to some of the hydrocarbons in its atmosphere. And so here are some of the more interesting moons of the solar system to scale with the Earth. And so once again, I like to show this because the colors make them pop out and look so different. And you can tell immediately that these moons have different environments from each other. So those are the planets, moons of the planets. But some of you are saying, Dr. Will, don't ignore Pluto. I would never ignore Pluto. And so actually, and Pluto is going to be the topic of next month's Sky Tonight, Pluto and other Kuiper Belt objects, because Pluto is too interesting to be a planet. It deserves its own show. But when the New Horizons spacecraft arrived out at Pluto and took these images, we were stunned to see that large smooth region, which is mostly nitrogen ice, actually, and the reddish coloration to some of the mountains. And then, so the reddish coloration, we'll also see that sort of orangey color on Titan, and also the reddish part of the top moon here. This is Pluto, and the grayish object is its largest moon, Charon. You'll notice how both of them have those reddish regions on them. They're from chemical compounds called tholins, which are organic compounds, and they have this coloration in large part due to interactions with solar radiation. And so, and that's also part of what we see in the reddish cracks on Europa as well. So we can learn a lot about objects in the solar system by looking at their colors, and perhaps there's no more prominent display of that than looking at the Earth and the Moon together. This is the Earth and the Moon caught together in the same frame by a spacecraft. This is not a composite image. And so we're seeing the Earth and the far side of the Moon. And what you're seeing here is the difference in the way these two worlds look due to the fact that the Earth's gravity was strong enough to hold on to a significant atmosphere, which means that we could have liquid water stable at the surface. Otherwise, we're both two objects at about the same distance from the sun and made out of the same stuff in terms of the rock. But the ability to keep an atmosphere that's significant enough to keep liquid water stable at the surface makes this amazing color contrast when you look at our two worlds. And that's just a little bit about what the colors of space can tell us. I'd love to answer some questions for you now. And I
Awesome.
believe you want me to stop sharing the screen?
Yeah, please do.
All right.
I
There
just
you
want
go.
to see your lovely face.
No.
Yes, we do. We do.
No.
So when you come to the Dome Theater, Lisa is standing in the back of the theater, more in the dark. And it seems like she prefers that over
It's
having
true. I actually had a student once who recognized my voice but had never seen my face. She's like, "Oh, you're the person that does the planetarium shows at the Fleet." Yep.
That's
Never seen me before.
so see, everybody who's done the virtual events, you're lucky. You're seeing Lisa in sort of person. All right, but we've got some great questions. I love that we have a question that actually refers to Star Wars Day, because what is a parsec? And how are parsecs related to light years, if any, if there's any relation at all?
There is a relationship. So a parsec is a distance, it's not a time. And the name is actually combining the word parallax and arcsecond. And so a parsec is the distance at which an object shows a parallax of 1 arcsecond. And you're like, what does that even mean? It's not hugely important, but there is a reason for the word. And it is roughly 3.3 light years. It works out to be.
Perfect. Thank you for that. And I'm going to launch the poll real quick before I forget, because I tend to forget that. And how hot is the surface of a blue star?
So don't get mad at me because I don't remember the temperatures of the things in Fahrenheit, because astronomers and physicists don't use Fahrenheit. But I'll give it to you in this scale. In Kelvin, the temperature of our sun is about 6,000 Kelvin, which is roughly 11,000 degrees Fahrenheit. So Fahrenheit is a number that's going to be bigger than Kelvin. So for blue stars, we're talking 15, 20,000 Kelvin. So significantly hotter than the sun. And so the relationship is very similar to Celsius to Fahrenheit. So almost a factor of 2, but not quite.
It still throws me that hot is blue.
Exactly, because
when I look at my
because it's our very geocentric bias, right? Exactly. When we think blue, we think water.
Yeah, and we think cold, right?
We think cold, but water tends to be bluish upon reflection because it's good at absorbing red, and so it reflects back more blue.
Yeah.
Yep.
Always gets me.
Yep.
What is the most abundant color in the universe?
All right, so that's kind of interesting, because in terms of what we see with our eyes, we take a look at galaxies. We mostly see starlight. And if you mix all the color of light together, galaxies tend to look white because it's the combined color of all the stars in them. There have been attempts to try to map what is the average color of the universe. And I always, the word that comes to mind is latte. It's sort of a not white, so not completely white, but maybe like you've put a lot of cream in your coffee or tea. And so that tends to be the average color of the universe, although not itself a color. Like I don't see latte stars, but when we're talking about combining the light, that's what we get.
Got it. I've got a question for you. I know we're coming right up at 8 o'clock, which is normally the end time of the event, but we also always go a little bit over.
Yep.
So we're going to do that today too, because I've got a question. So the gas and chemicals, you learn a lot about how they the light and the colors of those. Do you think there is, and maybe that's a stupid question, but do you think there is a possibility that we see something red and we think it's one specific gas, but it's actually one that we've never encountered before?
So no, that's a really interesting question. And there's some historical examples of when we thought we've discovered something new out in space, but we just hadn't seen it on Earth yet. So the most famous example of that is helium, first detected in the light from the sun, so named after the Greek god of the sun, Helios, about 30 or so years before it was discovered here on Earth. There was an element originally referred to as coronium because it was discovered in the corona of our sun, but it turns out to be iron. But iron with half of its electrons stripped off, which takes an incredible amount of energy. And so that's just not going to happen in your average chemistry lab. And then nebulium, there was a color, there was an element observed in nebulae that we hadn't seen the pattern of here before on Earth. And eventually we figured out it was oxygen, but in a state that we don't normally see it here on Earth. And so as of yet, we have not discovered something out in space that we haven't eventually figured out, oh, it's this thing. Just in, with the nebulium, with the oxygen in that state, it's because oxygen on Earth is always in such a, we tend to think of air as being thin, but not compared to how empty space is. And so elements can get into different excitation states out in space than you would normally see them here on Earth. And so we would not see oxygen in this state on Earth unless we forced it to be that way. So it's a really fascinating question. And it's one that I always like to talk to my chemistry colleagues about, because they're so used to doing chemistry at one Earth atmospheric pressure and room temperature. And everything else, space is anything but that. And you get different states of elements and compounds and stuff. It's kind of fun.
I think we saw your excitation or state talking about the Mars.
Sorry. I actually warned people on Twitter basically that I was getting very giddy prepping to talk about the helicopter. Sorry.
I must admit, and I don't know, audience, how you felt, but I watched the landing of Perseverance live. I had the stream on my screen, and it was a very emotional moment because you see and it was more because you see the crew at NASA, right? The landing crew.
Absolutely.
They get so excited and they're so relieved that everything worked, and I couldn't help but kind of feel the same thing.
I do. I get emotional every time too. I do.
All right, we have another question for you, Lisa. What is the material emitting light from the black hole picture from April 2019?
All right, so in that image, you're not seeing the black hole emit light, you're seeing the region around it. And in that case, you're actually seeing light bending around the black hole itself. So the gravity of the black hole, you're seeing what we call sort of a light sphere or a photon sphere of light around it. So it's actually not the black hole, but the region around, materials in the region around it emitting that light. And because although we like to think of black holes as being these giant cosmic sucking vacuum cleaners, the stuff around them is just going to obey the laws of gravity. It's just that they've got really strong gravity to deal with. So you can be further away and still orbit just fine. And so the material that's nearby emitting light, it's beaming that light around it.
Got it. Thank you so much. There's no more questions from the audience right now. And that's okay because we are at time. For anybody who knows or doesn't know, sorry, no, noise from the kitchen. The Mars helicopter actually had a San Diego connection. Hey, honey, can you hold off for a second? Thank you.
My dogs were just barking, so we're all good.
Yeah, oh, there you go. We have the San Diego connection because Qualcomm did one of the chips in the helicopter, and I think they might have done more, but I'm also not super knowledgeable about that. But I'm excited that San Diego actually plays a role in trying something that has never been done before, and I think that's amazing.
And Malin Space Science Systems, their cameras are on almost every NASA mission at this point, so there's almost always a San Diego connection.
It's awesome. I love it. Well, with that, Lisa, thank you so much for a wonderful talk tonight. It was super fascinating to learn something yet again every month. We learned something new from you. I appreciate that. And to everybody who joined us tonight, thank you so much for being here with us. I hope you're just as excited as we are that we are planning on moving this event into the Dome Theater again. And of course, stay tuned. We'll email everybody as soon as we know. And if you are subscribed to the Fleet email newsletter, you'll get the news anyways, but I'll try my best to keep everybody informed on what we're doing. With that, thank you so much. Stay safe and have a great night.
Bye-bye.
Bye.